Hello everyone, Dollar Store Neil Tyson here, and I'm glad to be back. I've just wrapped up a huge project that involved quite a few sleepless nights. But now the celebrating is over, and my focus is back on the science we see on the screen. It was science fiction that motivated me to open books and find explanations as a child. It led me to much deeper studies. Today I want to dive into the show Alien Earth. Overall, I'm enjoying the show, but it could have a bit more actual aliens in it. The show is taking enormous diversions from the core horror and action in order to explore typical Hollywood unfolding mysteries. But there is science on the screen, a lot of it. So I have to talk about how Alien Earth and many other movies portray space travel. Alien Earth presents some incredibly high concepts, and some of them actually hit pretty close to home for me, as much of my own stories touch on similar themes in androids and consciousness. The scientific inaccuracies in Alien Earth aren't so egregious that they harm the plot. But from an educational standpoint, I want to clarify a common misconception about space travel that so many science fiction shows get wrong: the idea of running out of fuel. Don't get me wrong, fuel is absolutely crucial for space travel, and yes, you can run out of it. But here's the key. It's generally not a big deal while you're actually between stars or planets. Once you're deep into your journey, you're essentially just coasting. So when you see a spaceship just coasting, like we first saw the USS Maginot, there is no need to see that engine burning. Unless you're actually still accelerating or decelerating, there is no need to burn fuel or expend energy besides your shields. Why shields, especially for a 65-year trip? Well, there is radiation in space, especially in solar systems. Stars are nasty. In interstellar space, there are cosmic rays coming in from all directions. All of it can be even more energetic, blue shift, if you're hitting the radiation head-on at near relativistic speeds. To make it worse, in over 65 years the exposure accumulates. By the way, you don't need high-tech powered shields. Using water in your hull does a good job. We also use water at nuclear power plants to block radiation more than we use lead shielding. And in space, you can also drink and recycle the water you use for shielding. In any case, this reduced requirement for constant burning of fuel is all thanks to the law of inertia. In a nutshell, the law of inertia states that once a spacecraft reaches its cruising speed, unless some outside force acts on it, it will continue moving in a straight line at that constant speed without using any more fuel. There's no air resistance in the vacuum of space to slow it down. This is a huge benefit. Once you've hit your desired velocity, you can simply turn off those engines and let inertia do the work, saving a massive amount of fuel. This crew had been asleep for the better part of 65 years, doing just that, saving its energy and supplies. However, inertia also presents a significant challenge. To slow down for a landing, or to change direction, you must apply a new force. This is why a spacecraft has to fire its engines again, in the opposite direction, to counter its own inertia and safely land. The bad news is that it can take just as much energy to stop as it took to accelerate. It might take actual years to slow down. The good news is that if the majority of your ship's weight on takeoff was fuel, you'll have consumed a lot of that, so you'll have less mass to decelerate, requiring less fuel, particularly if you have discarded your tanks, or even your solar sails if you use them. So it's important to have fuel as you approach any destination. It's like brakes on your car. If you use up all your fuel trying to stop, you might not be able to slow down enough to actually land without making a crater. And this means that taking diversions during your trip, even if it's a nearby planet that you stop to orbit, it's incredibly difficult and expensive, if not impossible, without ample fuel. So that unscheduled stop in Alien Covenant was a big deal. This wasn't the Starship Enterprise, which can take joyrides or send multiple shuttles to do it. The law of inertia flies against the scientifically incorrect scenario we saw in Avengers Endgame, where Iron Man and Nebula were apparently stranded at a dead stop in space. Alien Earth largely avoids the mistake of having the ship stop, or of there being a danger of it stopping simply because it lost some fuel, but the loss of fuel suffered from some very fuzzy logic. The immediate concern about fuel loss should be missing Earth or impacting Earth. Little else. The USS Maginot in Alien Earth had no reason to stop. It would continue indefinitely until it hit something, and that something was going to be Earth, which it ultimately did. So the real concern when the fuel started depleting in Episode 5's flashback wasn't that the ship wouldn't make it to Earth, but that it wouldn't be able to stop at Earth or course correct to it. It would simply overshoot and keep going forever. The chances of it hitting anything else in the vastness of space to finally stop it would be literally astronomical. And speaking of rescue ships, intercepting a vessel like that would be incredibly difficult. The ship would be traveling at an immense rate of speed, likely far beyond what a rescue ship could attain in hours, or even years. Unless it could be intercepted at the most opportune moment and towed with a powerful engine, it probably couldn't be caught, ever. Even AI makes the same always burning mistake. No spaceship would burn its main engines continuously while docking. It would slam into the space station. Beyond those always burning engines, the Maginot's seemingly flawless artificial gravity is canon, thanks to alien Romulus.
This is where we run into a bit of a problem.
But real useful gravity in the Maginot's timeline is highly unlikely. The story is set in the year 2120, after a 65-year journey, meaning the ship launched with this tech around 2055, a date most of us will live to see. It feels too soon, much like Blade Runner, featuring past off-world wars and human-like androids in 2019. In 2055, we'll still be debating climate change, not leaping to other star systems with androids and artificial gravity. Artificial gravity was moot anyway. The crew used sleep pods for the trip. There are 3 ways to simulate gravity on a starship. The first, a fantasy gravity emitter employed on the Maginot and Romulus. I can imagine the emitter pulling on your feet with a wildly different force than on your head. While this is technically true on Earth, the scaled effect is infinitesimal. On a ship-size scale, however, this tidal force could be wildly disorienting. 1 G on your feet, less on your gut, and a near-weightless head and ear canals. I can't shake the feeling that this kind of artificial gravity would have to be janky, and astronauts would complain about it. I'll take the rotating Mormon ship from the Expanse, the LDSS Nauvoo, over that any day. A third, more realistic method is a constant thrust design, also seen in the Expanse. A ship constantly accelerates to mimic gravity, flips at the halfway point, and then decelerates to its destination. The ship's entire layout must be bolted down and designed around this constant thrust vector. This is because on half the trip, your floor is your ceiling. We could use this technology today, but the fuel cost is the primary obstacle. The fuel would weigh far more than the ship itself, and be incredibly expensive to launch. At current SpaceX prices of roughly $100 per pound, a one-way, 1G constant thrust trip to Jupiter would require a conservative 140 metric tons of fuel launched from Earth orbit. A second issue with the show's physics was the ship's behavior in the atmosphere. The slow-moving craft, slower than a fighter jet, seemed to glide into its crash as if it had wings, despite being completely non-aerodynamic. While its forward momentum would prevent it from just dropping like a rock, it should have followed a ballistic arc downwards, instead of maintaining a straight line into the buildings. Although a faster speed would make the trajectory appear straighter, it would still be an arc. A truly straight path would only be possible at incredible speeds, and an impact at that velocity would have been cataclysmic, potentially releasing enough energy to wipe out dinosaurs. Critiquing the aliens themselves is difficult, as they're largely fantasy. The Xenomorph life cycle makes little sense except as a fauna-clearing weapon, meaning it kills all animals that could challenge it and then goes dormant, perhaps only extracting useful DNA or memories. Except for Alien 3, it doesn't eat. The Xenomorph is aggressive and doesn't communicate, but that doesn't mean it isn't intelligent. Its huge head implies a large brain, but one used for something other than language or tech. Perhaps it's a biological supercomputer, parsing a vast library of victim DNA. Such a library wouldn't take up much room. Because DNA is a molecule, a library of billions of samples could literally fit on a grain of sand and could be passed on. However, the processing power required to run simulations from that library, visualizing potential evolutions before it matures, would be monstrous. This intelligence could exist without any concept of science or biology as we know it. Each new xenomorph is a new generation, seeming to take on traits from its host without altering its core phenotype. That is, how it physically looks. It might choose to ignore the DNA of a mundane, non-tactical waterbound host, except to perhaps explore proteins used in venoms and store them. However, if it gestated in a fantastically advanced creature, say a superhero or Asgardian, it might make a significant evolutionary leap. It could adjust its physical form and cross-reference its entire genetic library to enhance this new version of itself even further. I know this last part got a bit out in the weeds, but I'd love to hear what you all think.